discussion? Okay, so let's take a vote then. All those in favor of Wednesday, raise your hand. All those in favor of Friday?
I actually have another example.
Okay.
Oh,
All right, well, I knew it was going to happen. It always does. We have someone that has an exam, but so the exam will be on Friday, which means that everything we cover up through Monday is fair game for the final. Not final. You're like, yeah, final. Let's go. Yeah. Everything up through what we cover on Monday will be fair game for the first exam. What we cover on Wednesday will go on to the second exam. Okay.
We do a partial review Wednesday at the end of class.
Yeah, so I will bring in a study guide and a study sheet or kind of the topics that we've covered. And I'm going to be honest with you, this first exam is an opportunity to kind of do really well because it's mostly building on what you already knew in fluids with a few extra key principles, right? So start well, I guess is what I'm trying to say. All right. Yeah, and so I will cover what the rules of the exam will be and so forth. Questions from those online? Just a reminder that it is expected that you will be here in person for the exam, unless you are sick, and then you need to notify me, and then we'll make arrangements for the syllabus on what to do on that. I will get an additional room for the exam because we all can't fit in here under the safe rules. So I'll find another room that we can split into two parts. So you should get plenty of room spread out.
Dr. Bruce?
Yes.
Yeah,
I'm not sure. I'm going to think about that.
oh, okay.
I mean, let me give that some thought. Okay, seems to me there was something else I was supposed to cover.
What was the question?
Oh, thank you for, yeah, the question was, will a formula sheet be allowed for the exam? And I don't know yet. Okay.
If it's not, will you provide some formulas?
So, yeah, so the question was asked if one is not allowed, will I provide one? Once again, I'm going to think about that. I will provide all the data that's needed. I don't expect you to memorize things like viscosity. I do expect you to have the specific weight of water and the specific, gravity, specific density of water, if you will. I mean, those are values that should just be up here. And the other equations that we've had, it's pretty basic. The change in pressure. There is a few fluid properties equations, the Bernoulli equation, momentum equation, and I just reminded me what I need to talk about again. So I'll think about it. I doubt that I will allow a full sheet. If anything, it might be a 3x5 card. And I need to clarify 3x5 inches. Because we laugh, but I did have a student bring,
No way.
yes, 3 foot by 5 foot piece of paper into the exam. Didn't help him any. He still fell. He tried to cram every little single homework and example onto that piece of paper, and rather than learning the material, and didn't do well. Anyway, so it's kind of funny now when I think about it, right? Put all that work into it, and should have spent that time studying. So the other thing that I thought of, and Scott pointed this out to me, I appreciate him catching my mistake. And I'm also trying to push to get all the solutions posted. The solutions I have are posted. Those that are come from the book, I asked the grader to post those. We did find an error in one of those in the first problem, first homework assignment, I think. The bigger mistake is on the thrust block. I had some signs incorrect on my solution in the Y direction. I just made a mistake, and so I haven't had a chance to fix that. I'm hoping to get to that today, to fix that and repost the correct solution for the thrust block. Okay. And I don't know if the graders even looked at that. If you did lose points on those, you know, you're more than welcome to contact me and I'll work on getting that change. Okay, if there's no other questions, then let's dive into some new material. Okay, so we should be able to see the screen. All right, so we finished up last time talking a little bit about losses in pipes and flow rates and sizing pipes. We talked about controlling the flow. And if the pipe provides too much flow, we said, well, let's put a valve on there or a contraction to be able to control the flow. And so that falls into the category of minor or local losses. Okay. And these, I guess parentheses should be around the local, not around the losses, but minor losses, we've already defined equation-wise in this class. We said that the total head loss is equal to the friction plus then the minor. And we said that the minor equation, minor head loss, and is equal to K times V squared over 2G, or we could change that to K times Q squared over 2G A squared, where dimensionally this has units of length. So it is a head loss, just like friction loss. It has that units of length to it because the velocity head has units of length and K is dimensionless. K is the minor loss coefficient, all right? So minor loss coefficient. And we typically find K by looking it up in some table, you know, on the internet, in some book, from the manufacturer. A lot of times manufacturers will supply Ks for select items. You're probably not going to find it for, you know, a pipe elbow. If you go down to Home Depot, you have to pull that out of the table. But if you're buying a select valve, most likely the manufacturer's already had it tested, and they'll give you a K value, or they should if they're a decent manufacturer. Okay. So there, I want to note this because your book covers this in one section. There are other ways of finding the minor head loss, and they are actually more physical. They are more physics-based, use the momentum principle, but they're very academic, if you will. They're not very practical, and so it's better to just use what's used in practice. It's quicker, it's simpler, and it works. All right. So the part in the book that talks about the flow going through an expansion, and they do a momentum analysis, it's great to help understand fluid flow, but it's not used in practice. So whatever, I'm going to move this, and hopefully you guys, well, probably just need to see what's on the board anyway, not me. So if you open up your book, we have in chapter 4, table 4.3.1, minor loss coefficients for pipe flow. Okay, let me zoom in here a little bit. It's just not very focused, is it? Well, I don't know how to bring that in better focus, but so you've got 90-degree elbow at the top, regular. Let me zoom in on that. Maybe that'll bring it a little better. Okay, and you can see that there's a range. All right. Now, in the absence of any better information, you're going to take the middle of the range. Why would we necessarily take the extreme of 0.3. What would be the rationale of why not take 0.3 rather than say 0.25 or 0.26? I mean, we're engineers, we tend to be risk adverse. So wouldn't it be better to be more conservative and pick the higher value? And that argument is indeed true. It would be more conservative to pick the higher value, but the part of would it be better? Well, it depends on who you're trying to please, right? And there you go. Cost comes into play. It's very expensive to put pipe down in the ground. And so unless you have a valid reason, you don't want to over-design your project because you're going to cost a lot of money. It's going to go in the ground and it may not be worth anything. And that's why we hire engineers. You guys heard the definition or the difference in between an engineer and an architect? You guys ever heard that? No? Is anyone here related to an architect? You better check online. I don't see any hands. Okay, good. I can tell this joke. The difference in between an engineer and an architect, civil engineer and architect, is a civil engineer can do for $1 what any fool can do for 2, and an architect can do for 5. Okay? Now think about it. They like to do things really fancy, and I like to poke fun at architects, but you know, they actually do, they provide a good service. But for most of what we do as civil engineers, the second part of that joke actually has significant meaning. A lot of what we do, most people could do, given enough money, right? You want a road somewhere, could they go out and build a road if they knew how to work a dozer? Sure. Would that road last? Would it be high quality? Would, the cars, would it get potholes on it and all that sort of stuff? Well, probably. It probably would over time. So we know how to do things using the properties of the materials to last longer and to save money. Now, there are select things that we can do that they can't. And I'm not trying to diminish what we do as civil engineers. But building a building, you know, we throw up a beam. Well, could they just oversize it? Well, sure they could. Now, would that be as good as an earthquake? Maybe not, because sometimes when you oversize things, it's bad. So there still is this select area where they couldn't, but a lot of what we do, given enough money and time, yeah, sure, they could do it. Okay, so we want to save money, but at the same time, we want to make sure that it's safe, reliable, lasts. You know, we get a good life cycle out of it. So while I'm preaching the benefits of making sure that we use correct values here, reasonable values, not extreme values, I'm also going to share you another story because I don't get to teach the engineering hydrology class, and I used to be able to teach that one. Just being chair, you know, doesn't allow me the time to do that. But when I was working down in Louisiana at McNeese State University, I had a guy contact me. He was another engineer. He was a chemical engineer, reasonably intelligent, but he just built a house in a neighboring town in a new subdivision. And Louisiana, as you may know, has problems with flooding. Like Charles has problems with hurricanes right now too. It's, you know, heard you guys talk about wind, and it's been pretty amazing to see the wind that has occurred around here, because I've had some neighbors that has lost some trees and been picking up branches and stuff last couple of evenings. And, but I'm glad I'm not in Louisiana right now. I mean, we lived there, went through one hurricane, and have friends down there and see what they're going through now. It's way worse this time. But anyway, I diverged from the story. So they get a lot of water down there, all right? 40 inches a year, approximately, is what the rainfall rate is. So, you know, 4 times what we get up here. Brand new house, and had lived there 3 years and already had flooding issues out of the two of the years. Now, the flooding issues weren't terribly serious as far as they hadn't gotten in his house, but they'd come right up to his threshold of his door. He's like, this is not good, you know. These weren't even bad years. It wasn't a big storm, and he's like, we got to take care of this water. The developer wanted to build more houses, and had a plan, went in and wanted to get the plan approved, and some of the people that already lived there showed up and said, well, we think there's a problem, we need to resolve this. Well, if you remember, engineering hydrology, most of you, I think, have taken that. There's two methods to calculate peak flow, peak discharge. Well, there's more than two, but two common ways for relatively small areas: rational method and the NRCS method, right? Or the SCS. Depends on if you go back far enough, it's the SCS, or TR55 is another name for it. And both of them calculate peak discharges, and there are assumptions in each of them, all right? So he brought me the set of plans. So the developer went to what's called the police jury, which is essentially the county commissioners there. It's a different system down there. And they looked at it, and fortunately the county, or the parish, because they're not counties, the parish engineer said, well, you know, we got a lot of people complaining, so, I don't remember exactly, it's been too long, but I think he used the SCS method, or no, he used the rational method. And the county engineer said, well, why don't you go use the SCS method? So he did. Well, not only did he use parameters that were extreme on the other end. So rather than like the 0.3, he used the 0.21. And the SCS method actually proved to be less of a peak discharge. So when he wrote up his report, that's what he did. He said, I compared these two methods. This one, look what this one provides. It's half the flow of this one over here. So we want to use this one because it costs us less to put in infrastructure. Now you think about that, and so I explained it. This guy didn't want me to really, he wanted me to explain the concept and he was going to push it forward. So I did. I sat down and explained the two methods to him, and I said, this is borderline unethical to know that one method produces a certain flow rate, the other one's lower, so you're going to pick the lower one when you already know that there's flooding issues out there. Now, if you didn't know there was flooding issues out there, then I guess you could argue it. Like, yeah, I'd be a little mad too, you know. And I don't know whatever happened. We moved soon after that. But my point is this: use a little common sense. Realize that you have a reputation, your personal reputation, and so you want to do a good job on both sides of the coin. You want to save money for your client, but also make sure that the project is doing what it's supposed to do. Okay, so enough on that. Back to this. As we go down through here, you'll notice that butterfly valves have different K values. So that's based on how open they are. And that's true for all valves. The more you close a valve down, the higher the K value is going to occur. The higher the K value, and the more head loss through your valve, which means you're burning up energy in your valve, but then you can control the flow by increasing the head loss, okay? So you have to do a little bit of adjusting there. We've also got some stuff over on this page here for different expansion contractions. It can be based on the radius, so you have to kind of look at the diagram and say, all right, what is my radius compared to my diameter? And that's going to give me then my K value over here, okay? So our book has a reasonably good resource there. It's not complete by any means. And if we jump back to chapter 12, where we talk about pipe networks, they have a little more information here. Okay, yeah, they got pictures. So table 12.2.4, some more K values. All right. Here we have a 90-degree elbow standard, 0.25. So that fell within the range of 0.2 to 0.31, right? Or 2.1 to 3, I guess is what it was. We've also got pictures over here on the next page of the different valve types. And I don't want to spend a lot of time going through these different types, but gate valves are very common. They're just a gate that slides up and down, blocks the flow. The flow has to go underneath the gate. Globe valves are great for control flow. Gate valves are very good for the flow on or off. So it's either all the way down or all the way off. They're not necessarily built to be throttling the flow a lot, because if you constantly run the flow down a little tiny opening right there, And if cavitation occurs, it will eat away at the seal. So over time, if you could then try to close your valve, it won't close completely because you've eroded away part of that seal. Globe valves are a little better for flow control. A pinch valve is nothing more than like a rubber liner, and then you just squeeze it down. And that's also pretty good for flow control. Needle valve, these are a lot of what your valves are for outdoor faucets, or needle valves, or some type of a needle valve. They're just it's a different name for a globe valve. It's just a little smaller, and you come down and then you seal it off right there. Plug valves and ball valves, these are, if you've ever done a small system, a ball valve is just a ball that has a hole through it. And so when it's open all the way, it's like the pipe doesn't even have a valve there. It's a complete shot, straight shot. And then you can turn that ball, and that hole then turns, and flow has to move around through that, and that creates a constriction as well, okay? The other one that's important is check valves, all right? A lot of what we do, we want to make sure our water system's safe. So if we have something fail, let's say a farmer's out watering his cows, and he stuck his hose into the tank to water the cows. The tank, of course, the cows, they stick their nose in there and they get grass and all sorts of snot and other stuff that goes into the water. And over time, you get a lot of biological growth going on in that tank. And the cows call that flavoring, right? But if the system that hose was hooked up to, if that system failed and that tank happens to be higher than the rest of the system, you may get siphoning, reverse flow back into your system. No big deal, right? When the system comes back up, we'll flush it out. Well, maybe or maybe not. That water may move down through the system, and then when you go to turn it on, some of the bacteria sticks around, or some of the flow heads off in a different direction, let's say into the farmer's house. So they're getting a drink of water, and it heads down the other T and comes down in there, and now he's taking a drink of that flavored water, right? So we have backflow preventers, which are a form of check valves. A check valve then only allows the flow to go one direction, all right? And those are very important in a lot of different systems. Homes usually have them from the city. The water can go one way, it can't go back out in the city. Sometimes we have to have an air brake. Toilets are a lot of times this way, where when a toilet flushes, water going into the toilet is actually above the high water mark in the toilet. Now, some newer systems have gotten around that by putting the check valve actually inside the valve itself. But the older systems, it would fill and then it would come up, and the ball valve, or the ball level would come up and turn it off. But there was always an air gap there. So if there was anything that happened in the system, it couldn't siphon it back because there's an air gap. So air gaps are an effective backflow preventer as well. Okay. All right. So let's see how we use this. So let's go back to chapter 4. Go ahead and pull out a piece of paper, because we're going to have a little quiz right now. Don't get too stressed. I just kind of want to see how much you remember and how much you can pick up here. Okay. All right, and for those online, I will actually post a Moodle link for you to scan and upload this quiz. You put your name on there, and the question is this, all right? Given a contraction okay, and the contraction is going to go it's going to go down like this. So theta is equal to 180. Hold on just a second here. Actually, this is supposed to be 100. That's supposed to be 90. So that's 90 right here. So this is 90, okay? So this first column is where D2 is over D1. And we're going to say that the ratio of D2 over D1 is equal to, no, wait a second. I'm sorry. I'm trying to think through this too fast. This is the ratio of D1 to D2, the diameters, right? Okay. Theta is 180 degrees because the angle from here over to here is 180 degrees. So D2 over D1 we're going to use as 0.4, and we're going to let D1 equal 1 foot, okay? Therefore, D2 is 0.4 feet, and we're not going to worry about being too exact with is that a nominal pipe size or not, but 0.4 feet, okay? And the flow rate, Q, is equal to, yes, okay. Let me back out on this a little bit here. Okay, and the flow rate is equal to, let's do 8 cubic feet per second, right? So I want to know from you, what is the minor loss in this valve? Okay, so I want you to find H sub minor for this particular valve. And let me try to zoom back in on that just a little bit. While you're doing that, I'm going to add the link. Oh, this is not going to. Okay, so those online are going to lose this for just a second. So go ahead and grab your minor loss coefficient off of there really fast. I guess actually everyone's going to lose this. Can you see that okay? So theta is 180. So I crossed that out, but it is 180. Yes. We're trying to find the total minor loss. Total minor loss through this contraction, given this scenario.
time.
Yeah, just hang on to it for a second though. We'll talk about it actually. Yes. Should be in feet. If you've done it correctly, it should come out in feet. Okay, we need to move through this, so hopefully you've got this by now. Someone feel comfortable with their answer? Let's talk for a little bit, because there's something I'm trying to drive home with this particular assignment or this particular quiz, which by the way, you will hand in, but it's more of a, did I give it a good shot type thing. What do you think, Aaron?
Loss of 26.42 feet.
26, okay.
I got 36.43, probably the wrong.
Probably the what? Right, yeah, that's fine. Round up, that's fine. Anyone get anything different?
I got 27.
Okay.
I just rounded it.
No one got, let me see here. No one got 0.68 feet?
Yeah, I got 26 too, but I know that makes no sense.
Makes no sense. Why does that make no sense?
Just have to get 26 feet of minor losses in your diameter.
Okay. All right, well,
Subtract the 2
you subtract the 2? Okay.
from the.
So I should be looking online to see here. Did anyone online get the 0.4 or 0.68 feet? Can I get this to, no? Okay. Well, that's actually good because the correct answer is the 26 feet. Okay. But I know what you're saying. You know, it's like, wait, that just doesn't make sense. But so there's two things I wanted to show you here. And fortunately, it appears that everyone got past the first one. So looking at this, if I look at this, K is equal to, or KC for 0.4 is 0.42, right? Oh, I need to get that out of the way. Okay. So the minor loss coefficient you should have found was 0.42. All right. And then we say, okay, I'm going to stick this in the equation, but if we know that Q is equal to 8 cubic feet per second, do we use V1 or V2, the velocity upstream or the velocity downstream? And apparently you guys used the right one, and you did that because of what?
The equation.
The equation, good. So this is a pretty common mistake that a lot of times engineers will grab the value and they'll use the upstream value. They'll say, oh, on the upstream value, I got 8 cubic feet per second going through a 1-foot pipe. I can find that velocity, 10.2 feet per second. Stick it in, boom, I'm good to go. But that would be incorrect because this specific equation right here tells you to use V sub 2. But notice that if I go down to this one right here where we have an expansion, use V sub 1.
Use a smaller one.
Yes, as a general rule, we generally use the smallest diameter pipe. Okay, however, you want to make sure that you look at the reference you're using because sometimes the reference switch. For some reason, 95% of the time they use the smallest, which gives you the highest velocity. But some references like to be different and they say, oh, we're going to use the smaller one. And you get still the same value, you just have to use the proper equation that's correlated to the minor loss coefficient you get. All right, Aaron.
So if you're just using Q instead of a velocity, you use the equation with Q over area. We just use the area of the smaller pipe.
Correct. Yeah, you make sure you use the right diameter, the right area, or the right velocity. Yeah. Yes.
I use the K2 squared over 2K8 squared. So like for the diameter, is it always like D2 over D1?
Say that last part again. I don't think the diameter D2 over D1 is what you use to tell you which minor loss you want.
Okay.
So how much are we constricting?
Because like when calculating the area, that's pi over D squared, right?
Pi over 4 times D squared, but you have to use, Mark, you have to use the right D squared. You have to use the right diameter. Do you use the upstream diameter of 1 foot or 0.4?
How do you know?
Yeah, so you come over to this equation right here and see how that V has that subscript right there of 2?
Yeah.
That means come over here to the picture, you use the values D sub 2, V sub 2.
Okay.
So you always correlate that to that equation.
What do you usually tell us if it's a contraction or an expansion, or is that something we might have to figure out?
Well, I'll just give you a picture and then you have to decide.
So contract is smaller?
Contraction gets smaller, expansion gets bigger. Yep. Aaron.
So if, like you said, so you gotta pay attention to what they use, would the K value be different if they flip that around?
Yes.
And went with the bigger one?
Yes.
So we would have a different K.
We would have a drastically different K value. Yes.
So that's where you have to be careful.
Yeah.
So as long as the reference you're using shows that it's a higher velocity, it's gonna have the K value to do that.
Right.
Would you, on the test, give us a table like this?
Yes, I would.
or at least
I would either tell you the minor loss coefficient or give you the table. Don't expect you to memorize that. Okay. All right, so are we good on that? Let's get back to Samantha's other comment here that, wait, this seems a little bit odd, 26 feet of head through a 1 foot pipe that goes down to 4/10 of a foot.
Well, 8 cubic feet per second is a lot of water.
That is true. That's exactly why I gave you these values is because 8 cubic feet per second go through and 4/10 foot of a pipe is 63 feet per second. Now, I hope you never design a pipe unless it's a dam outlet that you only use once in a while. I hope you never design a pipeline that has 64 feet per second going through it.
Like high pressure washers.
Yeah, if it's at the nozzle and it's a special design hose, then I get that. But for a municipal water system, if you've got those kind of velocities, you got a problem.
Well, you have some pressure or water hammers to blow the system.
Well,
Yes.
then you'd need an 86 cubic foot truss block.
That's right. Imagine the thrust block with that going around the nozzle. That's exactly correct. Yeah. So, but this does highlight the fact that you can burn up a lot of energy with a simple change, and that's how valves work. So this is a simple contraction, and a valve is nothing more than a contraction, except for it's movable, right? You can slide a gate down, or as the flow is going through the whole circle, now it's going through this little piece down at the bottom. That's contraction. All right. So even though the velocity is extremely low in the pipe and we get really high velocities around the valve, valves are designed to take that, whereas a pipe wouldn't. But we can burn up a lot of head in a simple little structure. Aaron.
So how would a pressure reducer work, I guess, in a line?
Okay, so we'll talk a little bit about pressure.
Flow.
Yeah, we'll talk a little bit about pressure reducers when we get to pipe networks, but I'll give you the basic gist of it. A pressure reducer is another type of valve, and it is simply it's a disc. So you have a hole coming through your pipe, through your valve, and a disc that's on a spring. And when the pressure is low, then the oh, wait a second, a pressure reducer. I'm sorry, I'm thinking of, that's a pressure sustaining valve. A pressure reducer is like this. It's like a contraction, except for it's a valve, but it adjusts automatically to the correct pressure that you need. So if you need less pressure,
Flow and then allow it into a bigger pipe, is that how you reduce the pressure?
well, it's a globe valve. Most pressure reducers are globe valves of one form or another. Where did that go? Okay, so it's like here. And if the pressure is too high upstream for what you want downstream, then the globe valve starts to close. And by closing, it creates a higher loss coefficient, which burns up more energy, which then reduces the pressure downstream.
Would that also reduce the flow?
Over time, yeah. Well, not over time. Okay. The answer is yes, but not within the ranges that we normally work. Because if we reduce, if we have, so we set the pressure upstream, say 60 PSI, okay? But we know we can get spikes. And so it spikes up to 100, and we have this pressure reducing valve down here to maintain 30, all right? Well, it's set at a certain depth when it's 60 going down to 30, or a certain height. Now, when we jump up to 100, it gets smaller, and you say, well, does it reduce the flow? Not necessarily, because now we increase the velocity going through the valve to create more head loss. So we're still getting the same flow rate, but the pressure now is lower because we've just burned that energy up.
We're still using that energy equation.
Yes,
Conservation.
yes. If the downstream use is still, you know, one gallon per minute, we're still going to get 1 gallon per minute, because here's the thing. This is why these pressure reducing valves work. If we start using more than 1 gallon per minute, it means that the pressure drops below 30. And so what does that pressure reducing valve do? It opens back up and it allows the correct flow rate. So it compensates the flow rate with the pressure and balances those two out. Okay. All right. How much time? We got 4 minutes here. All right. So let me ask you another question here. We have a system now. So given a system, I'm just going to represent it as flow going in, flow going out. And I'm going to say the friction loss, the ratio of the minor loss to the friction loss is 10%. Okay? So we don't have a whole lot of time to talk about this, but the ratio. So 10% of our system we lose in minor losses. All right? And this is at a flow rate. Q is equal to, say, 6 cubic feet per second. If I raise, if Q goes to 12 feet per second, what does the ratio, what happens to the ratio? Does it go to 20? Go to 30? Does it go to 5? What happens to the ratio? When we increase the flow rate,
The higher your flow rate, the higher the friction loss.
They're both a function of velocity.
bingo, right there, okay? They're both a function of velocity, right?
Velocity squared, so that they should both.
They're
change
both,
at the same rate.
exactly. The friction loss is F, L over D, V squared over 2G, and the minor loss, sorry, I'm gonna zoom out on this. The minor loss is equal to K, V squared over 2G. Now, there's the potential that our friction factor could change a little bit because we're changing the Reynolds number, but let's not get down into the physics, you know, that tight. If we double the flow rate, the ratio stays the same because now our losses go up. We have more friction loss, we have more minor losses, but they go up at the same rate. Okay. Any questions on that? Okay, with that, then we're gonna wrap up minor losses. I'll give you some homework to do on those. Monday, we'll talk about energy grade lines and hydraulic grade lines, and then we get to move into pipe networks. Yeah, good stuff. So have a great day, have a great weekend, and I'll see you on Monday.
Do you want us to turn this in?
Yes, turn those in. You will get credit for doing them. Those online, I've given you 10 minutes to turn that in. If you have class and can't make it in that 10 minutes, then, send me an email, attach it to an email and explain what class you had later on when you have some time. And, yeah, otherwise, if I don't get a piece of paper on Moodle or in class, you don't get credit.
Oh, take a look there. Like, is that what she's at?
Thank you.
Hi, Dr. Savage. Have a
Hi.
good weekend.
Thanks, you too.
Thank you.
Oh, no. Hold on just a second here.